Alright, welcome back. In this, we're going to go over substitution and elimination practice problems. This is going to be the mega, giga, epic practice problem video. Alright, so we got 10 practice problems here, but here's what we're going to do. For every single problem, I put a list of key concepts that we're going to go over. I know it looks blank, you're not losing it. It's there, something's there. But we're going to go over some very key concepts that you should memorize when taking an exam. So, I made a grand total of $0 in the past 28 days. So I designed these practice problems so it increases in difficulty as we go on. And there will be trick questions, alright? So about half of these are not, okay, they're kind of designed to trick you, kind of not designed to trick you. I mean, like, okay, whatever, you'll see. For all the problems, give me all the major and minor products if applicable. Okay, let's do A. Here, we have sodium chloride as the reagent. This is a nucleophile, so we're going to be doing a substitution reaction. On the bottom, we have DMSO. This is a solvent. This is garbage. This is junk, okay? Professors like to put this stuff on an exam. You don't really even need it. You don't even need to put it, but professors like to do it because some students think it participates in the reaction. It does in real life, but as an organic chemistry student, you could not care less. Because people think that, okay, it's contributing somehow as like electrons and it does something, right? And then, you know, it's a mechanism. It does not. It doesn't do anything. It's just there to fool you. The second lesson, main thing you take away from this problem is this right here is the alkyl halide, right? So this is the carbon and this is the halogen. Notice the primary carbon that's in the question here, the alpha carbon, has a wedge attached to it and the halogen's on a wedge. When you have something like this and you do a substitution reaction, your answer needs to be an inversion of configuration. In other words, any wedges turn into dashes and any dashes turn into wedges. Okay? Do you guys want me to do the mechanism? Okay, here's the thing. I'm doing this completely unscripted, and I don't know how long this is going to take. So if I do the mechanism for all of them, I don't know, this could be like an hour-long video. Okay, tell you what, I'll do the mechanism if you like and subscribe, and also comment something. Then I'll do it, okay? So let's just do it. Electrons form the chlorine, attack the carbon, the alpha carbon here, and kick out the bromine. And this is an SN2 mechanism because this is a strong nucleophile. It is not weak. It's not water, it's not ethanol, or it's not methanol. If it's not either of those three, then we're doing SN2. And then our answer will be this, right? The chlorine replaces, substitutes for the bromine there, and we have an inversion of configuration. The wedge has now turned into a dash. You must do this. Professors like to do this. They put this exact something like this, right, on a test, and people would just write this as a wedge, right, and then the chlorine. You'll get the problem wrong. You must switch it. And you only switch it if there is wedges or dashes attached to the alpha carbon. If there was for example, if there's a dash here, for example, let's do here, right? If there's like a dash here and it was like a nitrogen, you don't need to do anything. You leave this as a dash in your answer. But make sure you switch this, because remember, we are attacking, you only switch the configuration on the carbon you're attacking. So anything that's bonded to that carbon, okay? Oops. All right, let's do B. We have sodium hydroxide here. So what are we gonna do? Sodium hydroxide is a strong base and a strong nucleophile, okay? So what does this mean? What are we gonna do? Well, this is when you have to look at the geometry of the molecule. We have a strong base and strong nucleophile, but we need to choose what we're going to do. Or if you're going to do both. You can do both, but you have to know when to do it in the proper circumstance. Here, we have a tertiary alkyl halide. This means that, not including the halogen bond, we have 3 branches coming off of this carbon. We have 1 branch, 2 branch, 3 branches. This is a tertiary alkyl halide. SN2 mechanisms do not like tertiary alkyl halides. They're against it. It's like they're allergic to it, okay? Only E2 will happen when you have a tertiary alkyl halide. So this means we're going to be doing an elimination reaction. We will not be doing a substitution reaction because once again, substitution reactions do not like, SN2 reactions, I should say, do not like tertiary alkyl halides. And we're doing an SN2 or E2 because this is a strong base and strong nucleophile. It's not water, it's not methanol, it's not ethanol, so we're not even thinking about E1 or SN1, right? So it's either SN2 or E2, and we decided it's going to be E2 because this is a tertiary alkyl halide, and SN2 does not like tertiary alkyl halides. So let me do the mechanism here. The first thing I like to do for elimination reactions, I think this will really help you, is identify the alpha carbon and all the beta carbons. The beta carbons are the carbons that are adjacent to the alpha carbon. Okay, so we now need to see which one is the most substituted and least substituted. Because usually when you have elimination reactions, you have two answers, the Zaitsev and Hoffman. This is not a sterically hindered base. This is a regular normal base, meaning the more substituted alkene, or the Zaitsev product, will be the major product, or in other words, will produce the most of it in this reaction. If it was sterically hindered, then the Hoffman, or less substituted alkene, is the major product. But in this case, the Zaitsev, or more substituted alkene, is the major product, and the Hoffman product, which is the less substituted alkene, is the minor product. So how do we figure out what is the major and what's the minor? Well, you look at every beta carbon and count how many branches are coming off of it. Do not count the bond from the alpha and beta carbon. That does not count. So for example, this beta carbon has one branch coming off of it. This beta carbon has 0 branches coming off of it. And this beta carbon has 0 branches coming off of it. So since this has one branch and it beats all the other ones, the bond between the alpha and beta carbon here, the double bond I should say here, is the more substituted version. And that will be our Zaitsev product and major product. So elimination reactions involve sacrificing hydrogen on the beta carbon. So let's do that. We will sacrifice this hydrogen because there is one there. We sacrifice this. The bond breaks, and then now the electrons go to the alpha beta bond right here to create a double bond. And then now, since this alpha carbon has more than 4 bonds, right, because you have 1, 2, 3, 4, and now this double bond, which would be 5, we must kick out the halogen. All right, that would be this answer. Right, we formed the double bond between this alpha and beta carbon. This beta carbon is right here. Right, so we formed a double bond right there, and that's what this is. And now the halogen's gone, right, because we kicked it out. Let's do the Hoffman product now. We can choose to either attack this hydrogen right here or this one right here. They're equivalent. They're the same. The molecule will look the same. So let's attack this one. Right, because this is the beta. This is the beta carbon. So the electrons attack the hydrogen. That's the first arrow. Second arrow, the bond breaks and forms a double bond between the alpha and beta carbon. And then the third arrow we draw is the bromine leaving. So now the double bond has formed between this alpha and this beta carbon. And we are left with this answer. Now the key concepts is you need to know when to do E2 versus SN2 given a strong base and a strong nucleophile, and you determine this by looking at the geometry. This is why it's very, very important to know the geometry and what can be done and what cannot be done. If you need a refresher, please look at my SN2, E2, E1, and SN1 videos. Sorry, I'm drinking my tea. Oh, it's too hot. Okay. C. This is a problem that I made up because I wanted to go over a very specific topic, and this is something that frustrates a lot of students. When they see a big, huge molecule like this, students tend to freak out because they see that we have an iodine here, we have 2 rings, and a nitrogen. So they think, okay, we must have to do something with the nitrogen because it's there, right? Or something with the ring. No. Think about this. Think about it logically. You've only learned reactions involving alkyl halides. So you're not going to be tested on stuff that you don't know. That would be completely unfair, right? And if that is the case, then the teacher should be reported, right? But you're not learning this. So all this does not matter in a way. We're only worried about this part right here, the alkyl halide. So if this helps you, this actually helps some students, is erase everything that's not important. Erase all this garbage. So you're left with a tertiary alkyl halide. Now, doesn't this molecule look so much more simple? It looks like a normal, regular practice problem you guys been doing, right? So you can just do the mechanism like normal and then get your answer. Just don't forget to include the rest of the molecule, right? And it's the same thing. The other concept that you must know, and this is super, super important, is tert butoxide. Tert butoxide is a nucleophile and it's a base. Both very strong. However, it is a sterically hindered base. What this means is this base is very bulky, it's huge. Okay? So, yes, it is a strong nucleophile. However, it does not want to react as a substitution reaction because it's so sterically hindered. We have a tertiary alkyl halide here. That's the first thing, right? Is SN2 does not like tertiary alkyl halides. The second thing is SN2 does not really like tert butoxide. It could work, but under the right conditions. But since we have a very sterically hindered nucleophile and the sterically hindered geometry, alkyl halide, SN2 will not want to work. If this was a primary alkyl halide, then that's an exception. Then tert butoxide will work. Okay, but it won't create that much product. But since you have a tertiary alkyl halide, that's one bad, and then we have a sterically hindered nucleophile, that's a second bad, substitution will not work. We will only do an E2 reaction here. There's also another thing that you must know. When you have a sterically hindered base, the Hoffman product, or the less substituted alkene, will become the major product. In other words, that's what you're going to make the most out of. So if you were given a test question saying identify the major and minor product, the Hoffman or less substituted would be the answer for this. This is only the case for tert butoxide or any sterically hindered base. This is usually the main one that you'll be tested on. So let's do it. This is the alpha carbon, this is the beta carbon, this is the beta carbon, this is the beta carbon. This beta carbon has two branches coming off of it. This one has 0 and this one has 0. So this means that the Hoffman product, or the less substituted beta carbon here, is going to be either here or here. I'm going to choose to do here because it's the same thing. You'll get the same answer. But this one's just closer to write with. So we sacrifice the hydrogen. This goes here, right, to form the double bond, and we kick out the iodine. We are left with this answer, right, with the double bond forming right there, and the halogen is now gone. Let's do the other one now, the Zaitsev one, which will be the minor product. Okay. Since this was the more substituted one, there's a hydrogen coming out of here, which we're going to use. Bond breaks and forms a double bond here between the alpha and beta carbon, and now this gets kicked out. And then we are left with this, right, with the double bond between this alpha and this beta carbon. So the key concepts is you need to know what to do with a sterically hindered base. And the other thing is, just really know that it's the same concept you've been doing over and over, no matter how big the molecule is. I had a professor who gave us this gigantic molecule on a test, right? And it was like some kind of medication. And I think it was like, the professor said like 80% of the class got it wrong. And it was just such an easy mechanism. It was like literally a simple substitution mechanism. But since it was a huge, gigantic molecule with a bunch of different atoms on there, people freaked out. And they're like, okay, there's like a phosphorus on there, right? And people were thinking, okay, we have to do something with phosphorus. No, it was just simple. You have to do something with the halogen. Right, let's do D. Okay, here we have DBN. This is very simple, actually. DBN is a base. It's a strong base. That's it. Not a nucleophile. It's just a base. DBN literally looks, so what it is, I don't have the actual molecule with me here, but I believe, if I remember correctly, it's this. It's like a ring, and then another ring with a nitrogen. Actually, it's on the opposite side, I think. Something like this. I'm okay. Something like this, right? I'm not sure if there's double bonds. I can't remember. But you're using the nitrogens, right, to do the attack. Okay, so the nitrogens have the electrons, which are going to attack the hydrogen. I'm not sure the mechanism for this one. But if you're given this, just know that it's the nitrogens that are going to be doing the elimination reaction here. Okay, so, and this is not sterically hindered. So we're going to be doing a normal E2 with Zaitsev being the major product. However, this is a trick question. Let's take a look here. And what I mean by this. This is the alpha carbon, this is the beta carbon, this is a beta carbon, this is a beta carbon. You can clearly see that this beta carbon has 2 branches, this one has 0, this one has 0, okay? However, you would be thinking, okay, the Zaitsev would be here, right? The alkene, the double bond would be here. That would be wrong. Because this beta carbon, remember, carbon can only have 4 bonds. So this has 1 bond, 2 bonds, 3 bonds, the 4 bonds. Remember, the double bond's a bond. There are no available hydrogens on this beta carbon. If there are no available hydrogens to do an elimination, then you're not going to do it. This would only leave this or this. So it's okay to have one answer. You don't need 2 answers. So we're going to do a normal elimination reaction. But there's not going to be a Zaitsev or Hoffman or anything like that, right? So attack. It's just going to be one answer. No major, no minor product. And that's what you would get, right? Because the bromine disappears, so no more bromine. Okay, and then the key concept is DBN is a strong base, and understanding you might only get one product, and it's completely okay. All right, let's do E. Oh, we have terp-butoxide. Dun 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 dun. Okay. However, we have a primary alkyl halide. So SN2 can work here. However, E2 will be favored, right? Because terp-butoxide is a strong base, and it's a strong nucleophile. However, SN2 really does not want to do like a reaction if you have a sterically hindered nucleophile / base. So you will primarily do E2 for this. You won't really do much of SN2. So what that basically means is that when you give your answers, the major product is going to be the E2 and the minor product will be the SN2 reaction. Okay? So let's do E2 first. Okay, this is the alpha. This is the beta. Once again, we attack the hydrogen from the beta carbon. This bond breaks, making a double bond here, and then we kick out the iodine. So we are left with this. And this is the major, by the way. So this is major. No Zaitsev, no Hoffman here. Now the minor product would be attacking this, kicking this out, and replacing it with terp-butoxide. So this right here, this entire thing is terp-butoxide. That's how you draw it. So not too bad, right? So the key concepts here is that E2 and S2 are both possible if the conditions are satisfied for both. And they are. Barely, but they are. The only reason we do SN2 is because this is a primary. Had this not been a primary, then you won't do SN2 at all. You're gonna be making if you do this reaction in real life, like 95% is gonna be the E2 reaction and like 5% will be SN2. So you have to be really careful when you see terp-butoxide. 99% of the time, I should say, 90% of the time, you're going to be doing E2 when you have terp-butoxide, unless you have a primary alkyl halide, then you're going to do both. Let's do F. Okay, here is a nucleophile. It's okay to have something like this. It does not need to be an oxygen or chlorine or a bromine or iodine, right, as a nucleophile. It's okay to have sulfur. Sulfur is one of them. So this is just a normal nucleophile, not a base. So you're going to do a substitution reaction here. So attack the carbon. the alpha carbon, kick this out, and then you are left with this. Now, even when there's a hydrogen attached to it, leave it protonated. So when you have a nucleophile, this nucleophile in specific, leave it protonated. There's a whole story why, don't worry about it. Just leave it protonated. I know in my SN2 video, I said always leave it, don't leave it like this. It's okay. For sulfur, leave it. So the key thing is know that the nucleophile does not need to be oxygen or halogen, and then the sodium is just there, right? So anytime you see a sodium when you're doing E2 or SN2 or SN1, E1, sodium does nothing. Just leave it alone, okay? Okay, here we have sodium hydroxide. And we have a primary alkyl halide. So what are we going to do? Well, this is a strong base and a strong nucleophile. However, we have a primary alkyl halides. SN2 love primary alkyl halides. And we have a strong nucleophile. So that checks both boxes. Remember, E2 does not really like primary alkyl halides. So it's going to be the minor product here. So let's do the SN2 first. Kick this out. And now we are left with the hydroxide there as the major. And let's do the minor, which would be our E2 reaction. Okay, once again, alpha, beta, hydrogen, sacrifice the hydrogen, so you can put a double bond here. And then we kick out the bromine. And then we are left with a double bond. Oops. There. We're left with a double bond, right? Because this bond goes away, so we're left with a double bond here. And that's what we're left with. So the key concept is SN2 is major, E2 is minor, because the base is not sterically hindered. Something like tert butoxide, which would be, a different case. So that's why the SN2 is major here, because we don't have something like tert butoxide and we have a primary alkyl halide. Let's do H. Okay, so this is sodium ethoxide, sorry. So what are we going to do here? So, sodium ethoxide is a strong base and a strong nucleophile. We have a primary alkyl halide. So this means we're going to do a substitution reaction, SN2, and it's favored, so it's going to be the major product. But it's also a strong base, so we're going to do an elimination reaction. So let's do it. Substitution, right? Yeah, substitution first. So, same as usual. And then we are going to be left with this. Okay, then that's the major. And let's do the minor, which is our elimination reaction. Alpha, beta, I know I sound like a broken record by now. But I promise you guys I'll do it. So, steal that, make a double bond here. Kick this out, so this bond now disappears. And now we're left with this. Alright. So sodium ethoxide is a strong base and strong nucleophile. Since it's a primary alkyl halide, the substitution wins. So it's going to be the major. It's going to be favored. Alright, this is different. Here, we have ethanol. This is a weak nucleophile and a weak base. So we're immediately thinking SN1 or E1. Or both. We have heat. Heat is the immediate giveaway that E1's favored. Okay, that's the immediate giveaway. We also have a tertiary alkyl halide which satisfies the condition for SN1. So we are going to do both. However, the E1 product will be favored because we have heat. Immediately, whenever you see heat, E1 wins by default. That is an easy giveaway right there, okay? So let's do it. Now, be careful when you do the substitution reaction because there's something that's different. But let's do the E1 first. So this is one where you actually have to draw out everything because there's a carbocation. When you do an E1 reaction, the first thing you need to do is the leaving group leaves. You don't do anything else. Leaving group leaves. So now you must redraw the molecule. You can't cheat your way like how I've been doing it. So carbocation, okay? Now we are doing E1, right? Okay, so this is the alpha carbon, beta carbon, beta carbon, beta carbon. This is the more substituted alkene, right? Because this one has one branch, this one has zero, this one has zero. So the double bond's going to go here. That'll be the major product. So once again, let me do it. Hydrogen. This one takes it, right? Double bond forms here. In no third arrow. So we are left with, whoops, I did not mean to show all that. Okay, you know what? It's okay. Well, we're still going to do the other reaction. Okay, so that's what we're left with. This is the major. Okay, so now we are going to do our minor product. Okay, how should I do that? Let me erase all this. Okay, so once again, leaving group leaves like usual. We're gonna attack this beta hydrogen. Okay, the double bond will form here, giving us this product. And now we have to do the minor product, which is the new the substitution reaction. This one's different because you need to do an extra step here. Okay, so once again, carbocation. So that's where the ethanol is going to attack from. Now, when this happens, you are left with this. This is protonated. The oxygen has a positive charge here. This is not good. So what you're going to do is you have to redo the reaction here with ethanol. And this is going to take away the hydrogen here, stabilizing the carbocation, and that's how we're going to get this. Okay, so same thing, right? It just I removed the hydrogen. So now it's just the oxygen and the ethyl group. Okay, so if you see heat, think E1, E1 if the reaction involves a nucleophile. And then you must deprotonate it if the oxygen has a positive charge here. All right, let's do J. J is probably the hardest one here because there is 4 answers. Okay, this is a strong base and a strong nucleophile, so we're going to be doing both. Because this is also a secondary alkyl halide. Secondary, so there's another indication that we're going to do both. We have our alpha carbon here, and notice there's a wedge. Uh-oh. So here is something you need to know. When you do a substitution reaction, just like letter A, the first problem we did, when you have an alpha carbon that has a wedge or a dash, you need to do inversion of configuration when you do a substitution reaction. When you do an elimination reaction, you need to draw all the configurations. And what I mean by that is you need to draw this trans and cis conformations. So how do we do this? So let's do the elimination reaction first. This is the alpha, this is the beta. And this is the beta too, okay? This is more substituted than this one, right? Because this has 1 branch, this has 0 branches. So the Zaitsev we're looking here, okay? So let's sacrifice that one first. do this, and do this. Okay. Now, drawing the trans and cis tends to confuse people. So here is the trick. Let's just think about that this reaction's done, right? So we are left with this bromine, which is now gone, right? So this has gone, right? And then we have a double bond here. Doesn't this look a little strange, right? This would be the complete molecule, right? But doesn't this look a little strange, right? With this piece going down. So to fix this, just erase this, because remember, think about this. This carbon is no longer chiral. We drew it with a wedge because it was chiral. It is no longer chiral. So we don't need a wedge, and we can draw it normally. Like this, okay? We can draw it like that, because we don't need a wedge anymore, and we can draw it like a normal molecule, right? Because you go up, down, right? Like a zigzag. Okay, this is the trans version of it. The cis version would be like leaving it like this, but drawing it without the wedge, right? Because you don't need the wedge. This would be the cis conformation. So this would be the second answer. The trans configuration is the most stable, which is the major. It's always going to be the major, I believe, almost always. This is the cis conformation. So you need to draw it both. So remember, the first time you do it, right, when you get something like this, right, make sure you draw it. Okay, I did not want to do that. Okay. Well, draw it like erasing the wedge, because you don't need the wedge, right? And then draw like a normal molecule, like a zigzag. And then the other version is erase the wedge and then just draw it downwards, like a downwards line. And that would be the cis. Okay. Now let's do the less substituted version. There is a beta hydrogen here. Steal this. Bond breaks to make a double bond here. This gets kicked out. So in like the other version of this, right, to draw it properly, is erase all this, right? And what the molecule, the answer would look like is this. Okay? Because we formed the double bond between this beta carbon and this alpha carbon. Alpha, and then the double bond's right here, right? And the halogen goes away. Okay. Yeah. Now let's do what am I trying to say? The substitution reaction. Sorry, I'm losing it. All right. Okay, and that's it. I mean, we substitute with hydroxide. So that's the first one I told you about, the trans. That's the cis. This is the Hoffman. And then this is the minor. Oh, I forgot something. Aha, see, I make mistakes too. I forgot you had to do inversion of configuration, even though I talked about it earlier. So this is important. Even though that the group that we're replacing is not on a wedge or a dash, we are still attacking the carbon that has a dash. I mean, that has a wedge, right? We're attacking this carbon that has a wedge. Even though it's not part of the bromine, or where we're doing the substitution reaction, we're still attacking it. So that means we have to switch it. Oh, I almost, sorry. So yes, teachers can make mistakes too, right? Okay, the key concepts. This is super important. If the alpha carbon has wedges or dashes, if you're doing a substitution reaction, you can do the inversion, right? So all wedges become dashes and vice versa. If you're doing an elimination reaction, you need to draw all three answers. The major product, which is the trans, most of the time, and then the minor products, which is cis conformation, the Hoffman version, okay? And we got done in 34 minutes. So let's go! Alright, if you found this video helpful, please like and subscribe. Until next time, later.